Hello, and welcome to today's webinar, organised by the Analytical Scientist and the Activated Research Company. I'm Matthew Hallam, Editor of the Analytical Scientist, and I'm delighted to be moderating today's event, Innovations in GC that Increase Analytical Capability and Productivity. Just a note before we start, you'll be seeing some polling questions coming up on your screens from now. If you have pop-ups blocked, you might want to unblock them so that you can join in with these. Now, just let me start by introducing our fantastic speakers, Jim Luong and Andrew Jones. Jim is a fellow scientist, analytical science, core R&D of the Dow Chemical Company. Some of his key research areas include selective detection, ultratrace analysis, 3D printing, microfluidic-enabled gas chromatography, hyphenated techniques, and differential ion mobility spectrometry. Luong is a recipient of the 2007 Alberta Institute of Technology Award of Distinction and the 2013 Canadian Society for Chemistry Maxim Award. Recently, he was named in the top 100 analytical scientists on our own power list. And we've also got Andrew, who is CEO and co-founder of the Activated Research Company. Andrew's research and product developments focus on the nexus of chemical reactor engineering and analytical chemistry, with a focus on catalytic techniques that transform molecules for improved detection. He's the inventor of the PolyArc system, is recognized by several awards, including an R&D 100 Award, an Analytical Scientist Innovation Award, and Best New Product Award from the Gulf Coast Conference. Andrew is a recipient of the 35 and Under Young Entrepreneur Award, Techne Award, and Astronaut Scholar. So Jim and Andrew will both be on hand to answer any questions you may have at the end of the webinar, but please remember you can submit questions at any time throughout the event simply by clicking the Ask a Question button. Now, without further ado, let's get the webinar started, and take it away, Jim.
Thank you, Matt, for the kind introduction. And good afternoon, good evening, and good morning to all. I'd like to express our thank you for taking the time to join us at this webinar. I'm sure you will agree with me that productivity is an aspirational vision, regardless of whether we are in industry, academia, or in our real life. Nobody wants to waste time, as time is what life is made of, and time is not infinite. Today, we'd like to report to you a strategy our team has been pursuing over the past few years. We harness the synergy of innovative manufacturing process, such as 3D printing, with the power of chemistry via catalysis and post-column reaction to substantially improve the method performance based on the popular flame ionization detection, and in so doing, enhance lab productivity. I am presenting here on behalf of all my co-authors from Dow at various locations whose names are listed here. So as an outline to our presentation, slide will take a little bit of time to build. First, we thought it would be worthwhile for us to look at why 3D printing is interesting in the manufacturing process. Then we'll focus on catalysis post-column to improve performance of the popular detectors, such as an FID, the one-stage approach via reduction, the two-stage embodiment via oxidation and reduction. We examine the performance, and we'd like to highlight to you how this strategy can be brought about to solve challenging real problems that we are facing in gas chromatography. And together, we'll draw some conclusion, and last but not least, it's certainly acknowledgement. If we think about 3D printing, telecom has 5G, fifth generation of technology. Industry has Industry 4.0, and one of the elements of Industry 4.0 is 3D printing manufacturing process. It is an additive process. It can be quite efficient, on demand, unique feature set, so that you can instead of machining, you can produce it very quickly. And from our perspective, is perfect for prototyping. It is very popular, from printing toys to entertain your children to tools to amuse the scientists. Now, while polymer printing is relatively easy and there's formula to it, it is very difficult to do with metal 3D printing. Let me give you an analogy. It will be like building a pyramid. Ancient Egyptians built pyramids for eternal life, block by block of stones, and they have the stone has support, as you can imagine. But just let's think for a moment. If we were to build a pyramid with metal marbles, all spherical in shape, all same size, that pyramid is not going to be very high. So we need something to really anchor the material. So that something come in a solution that we managed to find is in the context of direct metal laser sintering. It is a technique that allows us to sinter and build layer by layer. So with 3D printing as an enabler and knowing that we use the knowledge in catalysis and post-column reaction, it is a perfect recipe for us to improve measurement of productivity in chromatography. And if we think about improving productivity in chromatography, where do we start? And the obvious choice is a popular detector, that's the flame ionization detector. So I'm quite sure without any doubt, you would agree with me that flame ionization detector is one of the most popular detector in gas chromatography. Just about any lab in the world will have one. Invented by McWilliam in 1957, co-invented by Harley, one in Australia, one in Africa. The detector has been proven to be a true workhorse. It's low cost to manufacture, it's highly reliable, simple to use, and the beauty is that it offers pretty high sensitivity in terms of performance. Typically, a chromatographer can get about 0.5 picogram to 1 picogram of carbon per second. But like anything else, it's not a panacea. The flame ionization also have some drawback, which we call it scotomas. The first one is in the space of the fact that the sensitivity of the FID vary from class to class of compound. And the outcome of that is that we need to have standard to calibrate. And standard can be expensive and cumbersome. The second one is that it cannot deliver carbon compound independent response, like detectors such as like atomic emission detector. This can be a powerful features. So once we identify the FID as a target for evaluation or for modification, the next question is, what application would we have in mind? So we think about many applications in FID, one of which is CO and CO2. It is highly popular. It's a popular request pretty well in any laboratory around the world. CO, CO2 are needed to measure from confined space entry to monitoring the quality of wine and beer that we're drinking. It is relatively easy to do at high concentration percent level, but it can be quite tough to do at trace level. Now, to deal with this, we borrow a CAM process that was innovated by Sabatier and Sanderer a long time ago. They simply took these two molecules and convert to methane through methanation process, and they use nickel as a catalyst at elevated temperature. 65 years later after the invention, Potter and Woolman brought this into the lab space, and actually they published the work in Analytical Chemistry as listed here. And today, the concept is commercialized by many vendors, commonly known as the Methanizer. The Methanizer worked well, no doubt, but due to the substantial extra hardware involved, inherently the gas chromatograph loses flexibility and become a dedicated analyzer. Every time we add part to it, tubing, union, flow controller system, it complicates the system. So once it becomes a dedicated analyzer, asset utilization and productivity will be impacted. So in collaboration with Dr. Jones' team in activated research, our thought was, why put up with the pain of losing flexibility? After all, we have hydrogen, we have heat, and what if we design a device that acts as a jet and at the same time behave like a methanizer? We can move it around from platform to platform. It is a consumable, so we don't have to tangle with the capital process. It's easy to install from GC to GC, and we can dial in the measurement on demand as a function of our workload. And as long as we have an FID, that should work quite well, right? And it fit most of the form factors for contemporary GC, and even for some that was not designed to have that capability to measure CO2, like the case of the Intuvo 9000, we can add that capability to the original gas chromatograph and make good use of it. So that's the concept. So how do we take from concept to design? Well, we built the first prototype of jet, and we check out its performance, whether the jet can actually perform in the envelope of a typical FID. And this plot shows the performance of CO and CO2 relative to a baseline compound such as ethane. And you notice that CO and CO2 can have pretty decent peak symmetry between 400 and 450 degrees C. And that's perfect because that's within the range of a classic FID can operate. After all, we already have the hydrogen. Now that's just chart and curve. And the next thought would be, how does it look like in terms of proof of performance using a chromatogram? Here, you see two chromatograms. The top one with a standard jet, and the bottom one is with the Jethanizer. In other words, the jet with the catalyst. We don't detect CO and CO2 in the top chromatogram, and that's very obvious because CO and CO2 does not generate CHO positive in a hydrogen flame. But in contrast, the bottom, we see excellent peak shape for carbon monoxide and carbon dioxide. That's the two peaks are highlighted by the red arrow. However, there's a catch. If you look at the acetylene peak, the peak height of the acetylene peak is about half in the case of the 3D printed jet. So 3D printed jet is not ideal for acetylene analysis. It will really pursue sensitivity. I'll get back on this topic later in the presentation. Now, just switch gear a little bit. We'll talk about backflushing, about post-column backflushing. This is one of my favorite techniques in practicing GC. It is an elegant strategy, and it helps us improve GC separation speed and system cleanliness if we are not interested in the late eluders. So in short, once the analyte of interest elute from the column, as denoted at the light blue dot, the flow of the column is reversed. So all the unwanted compound that's stuck on the column come from the injection can be pushed back to the inlet and vent, as denoted at the red dot, at the dark blue dot, and the yellow dot. Now, to have this feature in the gas chromatograph, we typically need a purge union and an additional pressure source, such as a PCM, a PSD, or an oxpack, which all add cost substantially to the apparatus. Now, what I would like to highlight to you is how you can conduct an in situ backflush using a Jethanizer concept. In this case, with the Jethanizer, we have a partial restriction in the jet due to the catalyst, and that can play to our advantage. So in order to conduct backflush using a Jethanizer, we simply drop the inlet pressure down and increase the detector hydrogen flow. The hydrogen flow split into two streams. Some will go and satisfy and keep the catalyst in a reduction mode, keep the flame lit, and the rest will flow backward onto vent and subsequently into the inlet and then out to vent. So this is work very good with short column of less than 30 meters and with diameter greater than 0.3. As far as we know, this is the first to report of a team that using the fuel gas of an FID to conduct backflush. And the beauty is that it does not cost you anything more than the jet itself. No purge union, no PCM unit. So it's a good value proposition to drive this technology. So to illustrate to you the application of the Jethanizer, we thought planes and cruise ship nowadays are a nice petri dish to study disease like the coronavirus because they are confined space. So confined space is a good way to study the presence of CO2. So we found that at elevated level of CO2 can impair cognitive process. So if you're a little bit sluggish in the plane, it might not be just because of the altitude of beverage. So just for the fun of it, in a number of commercial flights across North America, we took cabin air in the front rows, in the middle rows, and in back rows, and we analyzed it quickly. And what we see is pretty consistent that we saw air in the front row have lower concentration of CO2 than air at the back rows. Now, OSHA guideline is 5,000 ppm volume. So we are nowhere near the value of limit set up by OSHA. But Transport Canada is relooking at this because what they found is the concentration of CO2 higher than 1,000 ppm in flight simulator. They noticed that the pilot can do the routine quite nicely and on time. However, if there's an emergency like a blow-down engine or they have to abort the flight, it took the pilot a lot longer time to do that. So regardless, next time when you travel, maybe this is a good alibi to ask the leader to let you get a seat in the front row. Perhaps you'll arrive at the destination with a lot fresher mind. But that's methanation. And what else can we do with a Jethanizer? One of the applications we proved that is that we can convert CO to CO2 by methane via methanation. Perhaps we can take this strategy and do that via hydrogenolysis, formaldehyde and acetaldehyde detection. Formaldehyde and acetaldehyde are molecules of significance in many industrial processes, pollution chemistry, smog formation. It is tough. It's a tough analysis to be done directly without derivatization. And we do that on the FID. We have very poor sensitivity for formaldehyde because it's not making any CHO positive. So if you look to the inset of the graph, despite the fact that you see there's a slight improvement in response for methanol using the Jethanizer, you see substantial improvement of sensitivity for formaldehyde and for acetaldehyde as well. And in other words, you can use this strategy, can directly measure formaldehyde and acetaldehyde in the gas phase. I guess the next topic we're going to talk about is the two-stage. One can argue one is good, then two must be better. And while this reasoning might not be true all the time, but there is a method to the madness here. The Jethanizer focus on the simple process of reduction. Here we can have both combustion as well as reduction. We simply take the carbon-containing molecule, oxidize it completely to CO2, and then take CO2 with appropriate catalyst back to methane. Now, the question is, what would be the value proposition of doing that apart from the fact that we incur more costs? Well, the benefits are twofold. First of all, we have the capability to enhance the FID sensitivity and expand the capability of the FID. Compounds that are not sensitive to FID, like carbon disulfide, like formic acid, all of a sudden now have a response. And that's how we can increase the capability of the detector without really incurring loss of cost buying a selective detector for that application. But what we really gain is a carbon compound independent calibration that I alluded to you earlier. That allow us to quantitate compound without standard. Either that compound can be unknown or unreliable or perhaps toxic. So what the proposition here is, I don't need to work with benzene. I can go pick hexane. If I don't have hexane, I can find acetone. And I think the fringe benefit associated with that is effectiveness, productivity, and cost. I'm quite sure if you walk into any gas lab around the world, you'll see a rack as a picture depicted on the left-hand side here. Many standards. Individual standards are most accurate. That's why folks use a lot of standard. If we want to save a bit of cost, then we have mixed standard. And you can save some cost, but there's still a lot of bottle lying around. And these standards, the gas company conveniently put expiry date on it. There is even expiry date on hydrocarbon. But we don't conform to the expiry date, we potentially have a violation on the procedure. So this is a big amount of cost going to that. But what we're proposing is what we would do with all the standard. Instead of the rack on the left-hand side or the bottle on the right-hand side, what if we just calibrate our process with one standard, taking advantage of the detector capability that we have? This could be a value proposition in cost benefit. Very noble ideas, but we'll say, okay, how are we going to put it together? From a design standpoint, certainly with this device, we can have it at the detector's end, front or back, doesn't matter. We had it in a valve box. We even have it in the inlet. And in fact, the manufacturer provided a independent temperature control and flow control unit. You see the flow control unit in the top picture perching right by a polyarc reactor. So my point is you can have it mounted pretty well anywhere you so wish. So it's very scalable and very flexible. So, okay, what about the proof of concept? Many catalysts talk about having that capability, but it's like a holy grail. We're chasing it. Take a case of nickel catalyst. 35% nickel on chromosome W, make an injection hydrocarbon. You'll see that by the time you get to C6 and C7 and C8, you no longer have peaks. You have lumpogram. You have these very broad peaks that span 2-3 minutes. Here, when we make the injection of a hydrocarbon ranging from C8 to C24, and we did this multiple times, actually 12 times, the peak symmetry is excellent. And why we pick C8 to C24 and is allow us to bracket the range of hydrocarbon that we normally encounter in gasoline as well as in diesel. So we're pretty happy with the outcome. So with that, what else can we do with it? Because we talk about equimolar response. So the first equimolar response we would like to study is hydrocarbon. Here you see just alkane, alkene, and aromatic relative response to hexane. It is almost quantized at 1. Now that pesky acetylene come back up. It got better. Do you remember there was about 50% reduction in sensitivity? Now we're still seeing about 30% reduction in sensitivity. There's something to watch out for. So if hydrocarbon is good, then what about other components like oxygenated? And we conduct a full-scale study looking at primary alcohol, aldehyde, ketone, and we push it all the way up to ethylene glycol. It's a diol with high boiling point, and we all know it's pretty sticky. And in terms of response factor, it is quite impressive in the sense that we're within plus minus 10%. We're actually within range. Now, the next slide, waiting for it to come up. The next slide is actually one of my favorite slides, the whole slide deck. It shows the two-dimensional improvement of the two-stage reactor over of a standard FID. Now, instead of focusing and trying to read off the name, if you could just look at the red bar across the x-axis, just neglect the green bar. Can you see the gaps occur? That is the limitation of the FID that I shared with you earlier. That is the limitation that McWilliam and Harvey did not resolve. Now, if you look at the green bar, you see how it fills up all the red gap? So a molecule like CO, CO2, carbon disulfide, formic acid can be detected. It makes FID holes again. Now, that's the x-axis, right? But if you look at the y-axis, second dimension now, you can see the improvement of sensitivity of many classes of compounds. Compound like oxygenated, compound like chlorinated. And now that you have a chance to look at the performance, we thought is relevant to show some tough industrial application in terms of single dimension, multi-dimension, and comprehensive two-dimension. So in the case of single dimension, we thought it would be easiest application to execute. We want to highlight to you a separation of oxygenated in case of methanol in a commercial hydrocarbon. Here, methanol can have negative impact on the performance of the catalyst downstream. We separate these analyses using an ionic sorbent column, a CP low ox, 10 meter 0.53, and an impurity of 4-vinyl cyclohexene is shown here. And here comes the beauty. We do not have to purchase a standard for 4-vinyl cyclohexene. We just simply take the response factor of the methanol and quantitate, and we know that the concentration is within plus minus 10%. Now, single dimensional is pretty easy to do, but what about multidimensional gas chromatography? Because of the fact, after all, we are adding restriction to the back, right? The strategy of multidimensional gas chromatography is a very powerful technique practicing in contemporary gas chromatography, is that we get better selectivity and separation by harness the power of two columns with two different selectivity, or better yet, two different separation mechanisms, like partition chromatography in combination with adsorption chromatography. The Dean switch is a very popular tool. However, balancing it can be a challenge, especially when we are adding additional microreactor to the end of the system. So to make it difficult for us in this specific configuration, our team add two, not just one. In one stream, you see the two-stage microreactor, a polyoid reactor, get integrated into the system, and the bottom one is a Jethanizer. So it is a product description of both Jethanizer and polyoid, and we're driving this stream with one of the most recent development that commercialized pneumatic switching device, the PSD. So the application we want to illustrate to you here is the separation of CO from hydrocarbon. And I think the first notion you probably have in mind is that, well, how tough is this? You can do that easily in single-dimensional chromatography like a divinylbenzene column. That said, though, you think about it, at low level CO, that's tough. Tough analysis because air and CO co-elute on the divinylbenzene, and the oxygen in air, if we were to use a methanizer or a Jethanizer, it will cause a false positive. So in this separation strategy, we combine a wall-coated open tubular like a PDMS column. The intention is to clean up the matrix and have a partial separation of these light components listed bottom here from methane to propylene. And then we cut or transfer these two peaks, 6 peaks, it actually looks like 2 peaks, onto a molecular sieve 13X column. Here you see the beautiful separation of the light hydrocarbon. CO is separated from methane. Molecular sieve 13X offer much better performance of CO compared to molecular sieve 5A because it's too retentive. Now, I did mention to you earlier about the positive, false negative, or false response of oxygen if we do this separation on a divinylbenzene. If you were to squint your eye and you look at the chromatogram on a molecular 13X at the mark about 1.1 minute, you see a little dimple. That's the oxygen effect that I'm talking about. So ultra-trace CO measurement, this has been is an excellent setup for the application. So what about another application in the context of using multidimensional gas chromatography twin system? Here, a very relevant set of molecules, contemporary, high impact, is the measurement of volatile aldehydes. direct measurement of aldehydes such as formaldehyde, acetaldehyde, propionaldehyde, acrolein in the gas phase can be difficult, if not impossible. Folks tend to go through the path of do derivatization, and that is okay. However, there's also a lot of constraints associated with those techniques. So our aspiration is to come up with a way to measure directly. Anything that we can measure directly is better than derivatization. So using this approach with an ionic liquid stationary phase in the first dimension to achieve partial separation, we then take that box, that red box, cut it and transfer it onto a second dimension, which happen to be adsorption chromatography now, divinobenzene, and you see the beautiful separation of all four aldehydes. So this is going to be a very critical application for all of us, not just for industry. So we thought, good, demonstrating the difficulty with MDGC as a technique in GC. 2D GC is quite powerful in separating the analyte from complex matrix. And while identification of these analytes can be carried out by mass spec, either a quadrupole mass spec or a QTOF or triple quad, whatever you have it, is relatively easy. Quantification is a challenge that might not be really defined and talked about because of the fact that what are we going to do separating these molecules, identify them, and and if we want to quantitate them, they just might not have enough standard to go around. After all, you see these beautiful dots on the color plot. So here lies the opportunity to incorporate polyart to deliver the performance. And I thought this would be a good one. And comprehensive 2D essentially offer a different challenge in the sense that the ultimate challenge comes from the extra column effect. Adding a reactor to a flow path, the 2D GC is not very forgiving. In fact, it is not forgiving at all. It generates peak width about 100 to 400 milliseconds. The low column flow are used to achieve the best separation possible to avoid dilution in the combustion chamber. So in both cases, not a favorable condition to minimize extra column effect, which we refer to as tau sub C. So in this specific application or configuration, what we like to show you is how we rig this up together. We use a PDMS column in the first dimension with low flow at EOF, 1 mil per minute, and we tie that into a thermo-independent modulator. Modulator is the heart of 2D GC. It obtains or it collects a fraction of the effluent on the first column and re-inject it on the second column at very fast rate. And the second column is a wax column, short one, and again, low flow, and we tie that to a polyart system. And essentially, the result that we have here is quite encouraging. The separation of a Canadian diesel fuel is coming up right away here. And I think that I'm quite sure you would agree with me that is pretty decent. We're operating at EOF with the modulator, and we have peak width in the second dimension about 400 milliseconds. So separation of alkane, branch, aromatics, as well as 1 ring, 2 ring, 3 ring, including the big peak at the back end that you can see that come from biodiesel, that's FAME. Now, while we still have some more work to do to continuously improve this technology, the result obtained are quite encouraging. So certainly, the technology itself is not a panacea. It has its constraint. You saw the first constraint is the fact that acetylene has lower but reproducible conversion efficiency. So it's important for us to make sure that the detection limit generated for the acetylene is suitable for the application that you have in mind. And because it's a catalyst base, we need to monitor the performance of the catalyst. But I do have some good news to share with you, though, is that the catalyst that we put in 3 years ago is still performing just fine. And that we have ran many, many matrix. But one of the matrix that we need to be careful about is silicon, so that silicon has a tendency of compromising the performance of the catalyst. So tracking the catalyst performance is pretty critical. So in conclusion, we hope that we managed to convince you that the performance of a conventional FID popular detector was successfully enhanced with novel and reliable ancillary device using single-stage and two-stage post-column reactor. The combination of catalysts with 3D printing is just a real game changer. The potential application associated with these two variables essentially is only limited by the imagination of the chromatographer, and the carbon compound independent response that we managed to achieve will make famous like detector like atomic emission is a big asset in improving productivity and lower the cost of ownership. So in terms of an acknowledgement, we'd like to take the opportunity to thank these individuals who have contributed so tangibly to the project, Activated Research for the awesome collaboration and the friendship and the invitation to speak to you. And GC is a great technology. We don't have to make it great again. But with your hard work and innovation, I think we can take GC from not just good to great, but from great to awesome. And with that, I'd like to thank you for your attention.
Excellent. Well, thank you, Jim, so much. That was an excellent overview of applications for the PolyArc and the Jethanizer. And in the last few minutes that we have left, I would like to expand a bit on what Jim discussed and talk a bit about the technology behind the analysis at Activated Research Company. So this term of reaction chromatography, of transforming molecules so that they can be more easily or more selectively detected, is something that we had a vision for when we founded the company. And we really wanted to improve chemical analysis using this concept of reaction chromatography and catalysis. Specifically, we found that all detectors suffer from the same weakness, and that is that they respond differently to different compounds, whether it's a mass spectrometer and it ionizes different species differently, or an FID that creates different numbers of CHO plus ions. You have a different response for different molecules that must be calibrated for with standards. So in the last few years, due exclusively to customer demand, we have expanded on the vision of the PolyArc with several other products that also rely on catalysis to transform molecules, either to detect them more easily, more sensitively, or more selectively. Jim discussed the PolyArc and several improvements to that to allow it to be used for two-dimensional GC applications. We also produced the Jethanizer, which Jim also discussed, which is the world's easiest and most robust methanizer, and also the simplest to use. We also have the isotope, which was requested for us from a customer who was using isotope ratio mass spectrometry to look at anti-doping in different sports, and they needed an easier, lower temperature way to combust analytes to carbon dioxide so that they can measure isotope ratios and determine if steroids or things like testosterone were coming from the human or from a plant base. And maybe the most exciting application that is coming out from Activated Research Company is the Solvere. And this came about when we first launched the PolyArc in 2015 at the Gulf Coast Conference. People came up to us and said, yeah, the PolyArc is great and all, but can you do this for liquid chromatography? The pain points are much greater. The detectors, if you look at a ESI mass spec, you can have response factor variations of a factor of 1 million or more. And many detectors have blind spots, such as the UV-Vis. So the need for a universal detector like the FID in the liquid chromatograph world was a huge pain point, and that was brought to us by customers. So this year we will be launching what we call the Solvair, which is a FID with a polyarc that allows for universal detection in your liquid chromatograph. So we're very excited about that. And then, of course, the OFID, we are generating a new lower temperature design for the OFID to allow for oxygen selective detection with a standard FID. So founded just 6 years ago, we've had several awards and global attention, but we are just getting started, and we have several other products that we are working on. The polyarc is our most notable and flagship product. As Jim mentioned, it very simply converts any carbon-containing analyte to methane for detection and for a universal carbon detection with an FID. It is available now from Agilent globally, so no matter where you live, we should be able to get you a polyarc on your GC. And the main drivers for people using the polyarc, of course, are to quantify without standards, whether the standards are not available or they become increasingly toxic or reactive. People can quantify without using those standards. It can also increase the sensitivity to select molecules, and you can use it to analyze very complicated mixtures is a big utilization for that. And then some of the smaller uses are for green chemistry to minimize the amount of solvents and standards that you use, as well as to increase laboratory safety in the same vein by minimizing exposure of your chemists to sometimes toxic molecules such as cyanide or dioxins, and be able to use the polyarc to quantify without those standards. We also have several customers who produce chemical standards, whether it's in the liquid phase or the gaseous phase, and they actually use the polyarc as the last check to confirm that the standard was created correctly and that it hasn't aged or become expired. So that's a testament to the power that can be used with the universal carbon response. So with that, I would like to open up for questions so that we can optimize the amount of time we have for questions. I do want to thank Jim Luong and the entire Dow Analytical team for their excellence and innovation. It's not every day that you get to co-present with a world leader like Jim in chromatography. And Jim, it's truly an honor and joy for me to present with you. I'd also like to thank the analytical scientists for putting this webinar on, and the entire ARC team for the innovation and work that we put behind these products. So with that, I'd like to open up for questions, if that's all right with the webinar team.
Yeah, so Matthew again here from the Analytical Scientist. Thanks both for your great talks, and I'll just start reading through the questions because I've had quite a few in. So the first one we've got here is, do fully halogenated hydrocarbons give a linear response as other compound classes?
Yes. Chlorinated hydrocarbon halogenated does give linear response based on the molecule that we have studied, particularly for chlorine.
Okay, great. And the next one then is, how can I prevent catalyst deactivation by large quantities of solvent?
That's an excellent question. We did not encounter any catalyst deactivation by solvent. We have done a substantial amount of study over the course of the last 4 years. The data is solid. And you go back to literature prior to the commercialization of the product, there's a model built around that. There is sufficient amount of oxygen to make sure that the solvent that combusts and convert to CO2.
Okay, and the next one is, since silicon can have adverse effect on the catalyst, does one need to control column bleed?
That's a good one. Minimization of column bleed in any case is a good thing. When I refer to the matrix, I'm talking about the large quantity of silicon, 99% silicon versus the column bleed, which is very minute. So a normal column bleed, I would call, will have no significant issue with the catalyst performance. But minimization of the column bleed is a good practice.
Okay, and another one here is, when using plot columns, especially the low ox, does the reactor and Jethanizer have problems with particles? And if so, how do you control particle generation?
That is an excellent question. The low ox is an ionic sorbent column, and it will generate particles. The deposition of the particle actually is not an issue with the reactor. After all, the reactor is a catalyst base.
Okay, fantastic. And another one here is, how do I know the polyarc will work for me?
Good question. The way you know that the polyarc works properly for you is look at the compound independent calibration and conversion. So compare that to, take a baseline compared to an alkane, and you can compare that response to that of an alkane and have a relative response factor. If that factor is within 1 plus minus 0.05, then you know you're in good shape.
Okay, great. And how much does the system cost is another one we've had in.
That's a question I will defer to Andrew to address.
Thank you, Jim. Yeah, so the cost depends on whether you need flow control or heating, but it's generally around $10,000 to get that on your system.
For the polyarc, right? For the Jethanizer?
For the polyarc. Yeah,
Yes,
for the Jethanizer, I'm not sure if that question was directed at the Jethanizer. The Jethanizer is around $600 to $700.
Okay, great. And moving on, the next one here we've got is, often oxygenated compounds at low levels can absorb onto the column or the inlet. So is there a range of equimolar response?
Sorry, I missed the question.
Sorry, I'll just say that again. Often oxygenated compounds at low levels can absorb onto the column or in the inlet. So is there a range of equimolar response?
That's an excellent question. The reactor can only does its job if the analyte delivered to the reactor in fine form. If we have a system that is active and absorptive, then you know right away, because the relative response is less than 1. It will be 0.7 or 0.8. So it is important to strengthen the front end and the column, and it's a perfect tool for us to use to study column stationary phase performance. For those of us who do method development or stationary phase development, purchasing a polyarc is a good thing, because you can tell right away whether that polymer is inert or not.
Okay, thanks a lot for that response. The next one I see is, how many injections does the catalyst approximately handle before needing to be regenerated or before needing to exchange the polyarc system?
We have used the first polyarc system that we have in place has been 2.5 years now. And on that system, we have ran thousands of samples. Granted, most of the samples are hydrocarbon base and is rock solid. But the manufacturer recommend that every 6 months, you can turn the catalyst bed in for a swap. I think your experience may vary, but our experience has been tremendously good.
Okay, thank you very much. The next one, it says, would it be beneficial for separating heavy fuels, and how do we do it?
I don't understand the question. Maybe Andrew?
Yeah, I can chime in. So for heavy fuels, of course, the polyarc won't improve your separation, but it will allow for the analysis. Jim showed up to C24, and we've gone up even higher, up to C44. So really, if you can get it to the reactor, if you have a GC that can get to the right temperatures and the right column phase, if you can get it to the reactor, we will convert it to methane for analysis, one thing to note when you get to really higher temperature columns is you get a lot of column bleed. No matter what the manufacturer is, when you're operating at 400, 450 C on a column, you're going to get a lot of siloxanes coming off of that column, and it will significantly shorten the life of the polyarc if you're holding at those temperatures for a long time.
Yeah, one strategy that you can use if you're not interested in the light end or mid end and it's just geared toward a heavy fuel is use a column that is short as possible and highest phase ratio as possible. Or deviate from using silicon as a backbone. So, for example, you can use Calibration, which is very thin film, high retention, run to 400, 450, at which point you do not generate column bleed, right, or less column bleed.
Okay, thank you both for that. The next one I see is, what is the advantage of the polyarc if my analyte is formaldehyde in large quantities of methanol over a TCD detector?
Sensitivity. With the polyarc or Jethanizer, formaldehyde can be detected at a concentration of 50 to 100 parts per billion. A TCD, in the condition of a TCD, a best TCD, what I'm seeing is 2 to 5 parts per million. So you can see the magnitude difference. The value proposition is that you can see very low.
Okay, and I think the last question we have time for today is going to be this next one. And the question is the polyarc universal carbon detector for GC a different item than the Jethanizer?
Sorry, you broke up there. I didn't hear the question.
Apologies. The question reads...
I can take this one.
Oh.
Yeah.
Yeah, so the polyarc is a different detector is a different add-on than the Jethanizer. So the Jethanizer is just a reduction catalyst, so that can just take CO, CO2, formaldehyde, acetaldehyde to methane through a reduction process with hydrogen inside of your FID. The polyarc is a separate reactor that has both combustion and reduction, so that it can take any organic carbon molecule to methane through a combustion and reduction step. So in short, the Jethanizer is just for CO, CO2, formaldehyde, acetaldehyde, and the polyarc is for those and everything else.
And I would add that the polyarc is the most robust of the two because you have a chance to undergo oxidation and convert all the carbon-containing molecule to CO2. So it is just a layer, you can think about it as a layer of filtration of any potential contaminant to the catalyst.
Okay, thank you both for answering those questions, and thanks as well to the audience for sending them in. Before you go, there's a few short questions that we have to ask for you, the audience, and hopefully these should start appearing on your screens now as I read them out. So the first of these questions is, are there any applications that weren't covered in which you have an interest? So I'll give you a few moments to answer that. And the next question, question number 2, is was this webinar useful? So there's a simple yes or no answer there, and I'll give you a little moment again. And the third and final question we have is, what other laboratory challenges do you struggle with that weren't addressed? So thank you very much for answering those. And this only leaves me one more thing to say, which is thank you again to Jim and Andrew for their presentations and to all the audience members for attending. Don't forget this webinar will soon be available on demand at theanalyticalscientist.com. And for now, it's goodbye from me. So thank you again, everyone. Bye for now.
Thanks, everyone. Have a wonderful day. Bye.
Yes, thank you, everyone. Bye-bye.